All right, first let's start off by putting in some more of our equations. So, of course, to just remind you that the first column are your linear equations, second column are your angular equations. So when we're talking about force here, we're talking about a net force, and we're talking about Newton's second law, where the net force or the sum of the forces have to equal mass times acceleration. When we are talking about angular motion, we're talking about torque. And torque is that tau is the Greek letter that we use for torque. And torque can be found by taking the cross product of the force acting on the object and the radius or the distance that force is from the pivot. So the link here between force and torque is the radius, but we can also find the net torque by taking the angular analog of mass, which is rotational inertia, and multiplying that by the angular acceleration. So there are two ways to solve for torque, and it's going to depend on what the situation is you're looking at. Rotational kinetic energy versus linear or translational kinetic energy. Of course, linear or translational is 1/2 mv squared. Rotational is 1/2 rotational inertia times the angular velocity squared. Work. All right, linear work, I'm going to change colors so it's hard for me to scrunch it in here, is the force times the distance over which it acts, or the displacement. Well, work, sorry about that. Work in rotation is just, our torque times the angular displacement. And that's how we can calculate work for rotation. Spring force, of course, was a minus kx, k being the spring constant, and x being the distance that spring is compressed or stretched. And a spring force, if it's for something in a circle, doesn't come up very much, is going to be the spring constant times the angular displacement. But this spring constant is a little bit different because, again, we have to have our units in check. So the spring force here has units of newtons per meter. The spring force the spring constant over here, which is a little bit different K. It's hard for me to write with this pencil. This has to be newtons per rads, I believe. It doesn't come up much with rotational motion, but you should know it's there, and that should be squared. Sorry, that should not be squared. I'm looking at a different problem. Morning brain. Spring potential energy is the one I was looking at. All right, so this one's going to be 1/2 k for the spring constant times x squared. Again, that x is how much you have compressed or stretched the spring. On the other side, it's going to be 1/2, but now that curly k, which I cannot do very well, times theta squared. Again, that doesn't really come up in AP Physics C. Linear momentum, we've talked about this. Mass times linear velocity. Angular momentum, rotational inertia times the angular velocity. Conservation of momentum means exactly that. It has to be conserved. So final has to equal the initial for both angular and for linear quantities. All right, force. This is a variable force. So this is a non-constant force. We can get that by taking the derivative of the momentum with respect to time. And we can get the torque by taking the derivative of the angular momentum with respect to time. Okay, this is like your impulse equation, which is force times time. but for forces that are not constant, okay? And total net work on a system, it's just the integral of the force with respect to the displacement. My integral sign did not come out very nice. Let me fix that. And for angular, it's just the integral of torque with respect to the angular displacement. And then power, there is a different equation you can use for power. Force times velocity can also be found by taking the change in energy over the change in time, or the work over the change in time. Well, you can do the same thing with torque, only you'd multiply it by torque and the angular velocity, and get power. Okay, so there's a couple of different ways to get those. I don't know if we talked a lot about period last time, but let's go ahead and do that. It's going to come up when we do simple harmonic motion. This is the time for one revolution. And we have an equation for it. 2 pi r over the linear velocity, or 2 pi over the angular velocity. Okay, so those are two ways to find the period. I just want to talk about a couple things that have been, I've had a lot of questions over, okay? I is rotational inertia. It's not impulse. It's a common confusion. Impulse is J. Anytime you see I, it has to do with something that's rotating or a system that's capable of rotating. Rotational inertia, the general equation for point masses is mr squared. If you have more than one point mass in the system or objects in the system, you just add up all of their inertias together. If you have something that's not uniform, it's the integral of the length of or radius of that squared dot dr. Okay, and these are on your equation chart the same way. Oh, sorry, not dr, dm. Brain fart. These are the same thing. It just is going to depend on what you're calculating. So you would use this one for point masses. For given inertias. So one you can look up in a table. And a person also falls into this equation. Okay. The integral is if they ask you to derive or prove. Oh, I can't spell prove. Derive or prove a rotational inertia. And I'm going to post a video of those derivations with the integrals. I haven't had time to make my own video. I found a decent one yesterday, so I'm just going to post that for you. That additional practice on rotational inertia, this is what they wanted you to use to prove the rotational inertias given in the table. All right, when we are talking about a long, thin rod, it has an angular rotational inertia of 1/12 ml squared. This L right here has to do with the length of the rod, not angular momentum. So you're going to have to look for context clues. So is it something where we're multiplying an rotational inertia times an angular velocity? Well, that means that L is an angular momentum. If it's in an equation squared, then it must be talking about rotation, okay? You would never square an angular momentum quantity for any reason. All right, I hope that is a little helpful. We're going to talk a little bit about torque now. Now, this is like a quick summary. It's in no way intended to replace the Walter Lewin videos or you looking up more information on your own, so just keep that in mind. Okay, so we need to talk about rotation. Let me find my rotation here. We did this. Okay, so we have several things that can happen when we have objects that are rolling or rotating. Okay, Now, we're going to talk about torque in two different ways, because we could have things balanced on fulcrums here, like we did last year if you were in AP1, where you had to find the mass of the meter stick and a mass of an unknown. But we could also have things that are rolling, okay? So we're going to talk a little bit about the rolling just to introduce it. But most of your practice today is going to be the first situation, okay? So these are both torques. So this one's a rotating rod, which a meter stick is considered. Okay, so torque in general. Let's talk a little bit about that. So this is the equation regardless of which situation you're in. It can be the force times the radius, and that's just the distance between the pivot point and the axis of rotation. Okay, and then F is just the force on the object that's going to make it rotate. So the force that either starts the rotation or the force that's keeping the rotation going, okay? If we're talking about a net torque on a system, just like with net force where it's mass times acceleration, the net torque is the rotational inertia times the angular acceleration. Okay, so these are going to be two important things to know, because we're going to be tying things together. Okay, so let's talk a little bit more about each of these situations. So the first one I said we could have is something like this. This is also your bridge problems. And we're going to go more into those when we do static equilibrium. But you're going to do some basic problems with torque like this today. So if we're in static equilibrium, you have to have your net force, or your sum of the forces have to equal 0. And your sum of the torques have to equal 0, okay? So when we're dealing with forces, we're talking about those vertical and horizontal, or the up, down, left, and right. For torques, it is the clockwise, which you'll sometimes see abbreviated CW, and the counterclockwise, CCW, okay? So in order to be in static equilibrium, static means you're not moving. And so static equilibrium has to mean that it is at rest and it has no rotation. You have to have both of those, okay? At rest and no rotation. So basically, when you're doing the linear, the sum of the forces in the x direction have to equal 0, and the sum of the forces in the y direction have to equal 0. And you have the same thing over here, only the sum of the torques, and you're going to either have you're going to have some that will pull clockwise and some that will pull counterclockwise. They have to equal 0, or the sum of your clockwise torques have to equal the sum of your counterclockwise torques. So you're going to see some examples today using a couple of these equations. I will walk through a couple of the initial problems just so you can see a couple of examples. But I want to talk about rolling motion real quick. So let's talk about the difference. Okay, so we have rotation, which would be something that is rolling. Okay, so rotation would be rolling either clockwise or counterclockwise. Okay, we have, I should have put rolling up here. Sorry. But we also, in order to get rolling, have this piece that is a translational or a sliding motion. Okay, if we add these together, that's what we see when we have rolling motion. Okay, the velocity center of mass is going around the center, and so rolling motion ties both of these things together. Okay, that's why when we have something that rolls down an incline, you have both of those rotational and kinetic energy. All right, so let's talk about that example. Okay, so this is a wheel rolling down. In order to have rotation, you must have friction if you're on a surface. If you don't have friction, you're just going to have sliding. Okay, so sliding means no friction. And you're just going to use Newton's second law for that. Okay, and then depending on the situation, what your force diagram looks like. If we're rolling, we must have friction. So let's talk about what it looks like for rolling. So our force diagram, of course, the gravitational force acts on the center of mass. But we also have to have this frictional force right here. And by the way, this is something that's rolling down the ramp. Rolling up the ramp will look a little bit differently. Okay. We should also put our normal force in here, just so that I'm not looking like I'm skipping that. We're not really going to talk about what's going on in the vertical direction because we know that there is no acceleration there. So, of course, we have components here, and the angle is here. So our vertical is the normal minus that, oops, not sine, cosine, minus that portion of the gravity that helps keep it on the surface. So my normal force has to equal mg cosine theta. What I want to talk about more, and I should have said that this is static friction because the sphere is not sliding against the surface. But I want to talk about how we would solve this for the acceleration of this object going down the ramp. So we have to look at the horizontal direction, which is going to equal mass times acceleration. But it's also that component of gravity pulling it down the ramp minus that frictional force. Okay, well now friction is what's providing the torque in this situation. So the torque is going to be that frictional force times the radius of the sphere. But torque is also equal to the rotational inertia times the angular acceleration of that sphere. So that means my frictional force times the radius, let me make my radius look more like a variable, has to equal the rotational inertia times the angular acceleration. We learned previously that linear acceleration is equal to the angular acceleration times the radius. So we can rearrange this to solve for the angular acceleration. And again, our goal is, since we can't combine linear with nonlinear or angular quantities, we can't add and subtract those. We can't put those in equations together. We either need to convert everything to angular quantities or convert everything to linear quantities. The rule is usually to convert everything into terms of linear quantities. So that's what we're doing here with this torque provided by the friction. So I end up with an equation for friction of the rotational inertia times the linear acceleration divided by the r squared. Because I can divide both sides up here by r to get that radius on the other side. And then substituting in my equation for the angular acceleration using linear acceleration. Okay, so now I'm going to take my expression that I now have for the friction, and I'm going to come back up to this expression. So now I have I'm going to tie these two together. So mass times the linear acceleration equals mg sine theta minus the rotational inertia times that linear acceleration divided by the radius squared. All right, and then it just becomes simplifying everything to get the linear acceleration by itself. So using algebra, I'm going to add the rotational inertia to both sides. And that's going to equal the mg sine theta, which is the component of gravity that is also that is contributing to the acceleration down the ramp. And I'm going to factor out my mass plus my rotational inertia over the r squared. Divide both sides by that piece of information. And I have now solved for the acceleration of an object rolling down an incline. Now, if they gave you the rotational inertia or wanted you to give your answer without the I and then plugging in your mass and your radius, you'll see some things will cancel out here, or reduce out, I should say. So that will come up in some of the practice problems. So when we get there, we will talk a little bit more about that. But that's basically torque for rolling motion. My next example will be for a pulley. Usually this will be in the context of a falling mass. So I'm going to have a pulley, only now my pulley has mass. Okay, so in AP1, our pulleys did not have mass, but in APC, our pulleys are going to have mass. So now that they have mass, it means that they are capable of applying a torque, okay? So that torque is going to cause a little bit of a slowdown in the acceleration of the falling mass. So, of course, we're going to have the gravitational force, and then we're going to have this tension force going up, okay? So the net force here is mass times acceleration. And the net force here is going to be the gravitational force minus the tension force, okay? Well, this is what we end up with. And we do not have an equation for tension. But we know now that our pulley has mass that our tension is involved in a torque. So we're going to find our torque by taking the force of tension multiplied by the radius. We can also find the net torque with the rotational inertia times the angular acceleration. So combining these together, just like we did a minute ago with the friction, and we get an expression that looks exactly the same because we have the same situation. We just took our expression for the torque in terms of the tension and our expression for the torque in terms of rotational inertia and angular acceleration and tied them together. So then we can use that in our equation. So mg minus the rotational inertia times the linear acceleration divided by the radius squared. And then you are just going to solve again for acceleration. So I'll let you see if you can do that part. And you end up with m over the mass of the block plus the I over the radius squared. It should be noted that this is the mass of the pulley. That is going to come into play in the rotational inertia piece, okay? So the rotational inertia piece is going to be where the mass of the pulley comes in, not our net force equations, okay? And then this whole thing has to be multiplied by G. All right, and then depending on what you have, a disc, a cylinder, a pulley, or a solid sphere, pulleys are considered solid discs. You're going to put that in for your rotational inertias, and you'll get some different equations there. I'm going to hold off on that until we actually do some problems like that. But at least these notes you'll have if you start finding some practice out there or something comes up. There is one more example that we need to go through, but we'll do that next time because I only have a few minutes left of recording time. I will do a couple of examples from today's practice. Today's going to be some really basic torque problems with some balancing beams and things like that. So if you have any questions, let me know. Have a great day.